Thank you for being here. Today we are having a double presentation, a joint presentation from Tobias and Lukas. Both of them are from the Technische Universität in Cologne, where I was this year during 6 months, and some of our students here are going as well next year. And they are going to present something that is very important for us because we are trying to get into the subject in the next year, that is bidirectional charging. So thank you very much for coming, you two, and the stage is yours.
Thank you. Yeah, thank you so much, Aline, for the nice and warm introduction. Yeah, my name is Tobias. I'm happy to be here in case of the ProBal project. And yeah, what we would like to present today is the topic bidirectional charging in residential buildings. And yeah, we do a simulation tool developing, it's in Germany. It was a little part of my PhD. And now in the last day, we get some data from Amanda. Thank you very much for that. So we can test the simulation tool here in Brazil to show the potential for bidirectional charging vehicle to home here in Brazil. Do you have a nice. So yeah, we are from the University of Cologne, as already said. And yeah, here's a little agenda, what we want to share today with you at the first short introduction about the concept of bidirectional charging and also the potential and the status quo from vehicle to home and vehicle to grid in Germany as an example. And then we later come back to the materials and the methods we used in the simulation tool. What is the database we have in Germany and what was the database here in Brazil, the modeling approach, and then we shortly show you the results from the German households and the Brazilian households. And at the end we want to conclude this and want to discuss with you the results and the further opportunities. So first, a little thing about me. My background are mechanical engineering, and I do my master in renewable energies. My research focuses on home energy management systems, for example, and I have a deeper look into smart home systems, for example, to use the energy more efficiency in a household, load management, for example, but also a little bit hydrogen in the last years. And that's a little part of my side. And now I want to give the hand to Lukas.
Thank you very much, and welcome from my side. My name is Lukas Hilger. I'm also from Cologne Institute for Renewable Energy. And just a few sentences about my curriculum. Also studied at Cologne University of Applied Sciences in the bachelor's and master's program in mechanical engineering and renewable energy, and did my PhD in the topic of energy efficiency in small and medium-sized enterprises. There I developed a kind of measurement concept, how to measure efficiently electric load profiles and also how to analyze these data effectively. My experience is more in the smart energy, smart technology for companies, smart metering and energy efficiency. And let's come to our topic today. So the question is, what if you could reverse the flow of electricity from the car back into the house or the grid? So we're talking about the concept of vehicle to X or bidirectional charging of battery electric vehicles. And to get a start into the topic, some motivational factors. Why should we, from the energy perspective, talk about the bidirectional charging and about the battery electric vehicle? Of course, from the energy perspective, you have a very large battery storage in the cars. So compared to the typical home energy storage or the BESS systems, with about roughly 10 kilowatt hours, we have a capacity of 50 kilowatt hours or even more, so factor 5 from the capacity side. So a huge asset for the energy, or huge energy assets for the household. So why not thinking about how to use it effectively in the home energy management applications or in the home energy management system. Some other factors are the trends. We all know that we get more and more prosumer households, that we have the transformation to an all-electric society. That means, especially in Germany, more heat pumps and less gas boilers, more electric vehicles, of course, more PV plants, and also battery storages, so all electrified. And we have the fact that a lot of vehicles are just parked a lot of the time and not used for driving. So when they are parked, why not using them in other applications? And to get more detail in the topic, some data from Germany. We have installed energy storage capacity in Germany of 7 gigawatt hours of stationary battery storage and 65 gigawatt hours already of cumulated electric vehicle battery storage. And you see here the trend from 2017 to 2022. It gets more and more every year, and the largest part is already the battery electric vehicles with 65 gigawatt hours, and the home energy or home storage systems make up about 7 gigawatt hours today. Alone the battery electric vehicles altogether make already more energy than the pumped hydro storages in Germany, and these were for the last 30 or 40 years the biggest energy storages in Germany, and we have already more energy in all electric vehicles than in the pumped hydro storages. Yeah, and today we have about 1.5 million electric vehicles in Germany, and one statistic I found said that 166,000 of them are already suitable for bidirectional charging applications. We see that in more detail later, but just as that as a general statistic. Some definitions to get into the topic. We have, if you talk about bidirectional charging, we have several applications. And the first one is vehicle to load or vehicle to device. The principle is that single consumers are supplied with the power from the vehicle. So it's providing electricity from the battery electric vehicle to the electric devices. Then we have vehicle to home. The BEV is connected to the wall box, for instance, in a residential building, and supplies energy to the household. So this is increased self-sufficiency and by reducing or shifting electric consumption from the grid. And the final goal is optimizing energy flows in the household or the building to reduce energy costs. And the third one, and also the most complex one, is vehicle to grid. In this case, the BEV feeds the electricity stored in the battery into the grid to provide flexibility options or services for the energy system with price signals for customers. So in the end here, you get an increased grid stability and security of supply and better renewable energy integration through the provided flexibility options. These are the basic applications when we're talking about bidirectional charging. In the next slides, we are more focusing on the vehicle to home application, because this was the part where the simulation tool is working. Some technical components, just to get it all together in one slide. We have the battery electric vehicle, which provides additional storage volume to the household, increases self-consumption rate and degree of self-sufficiency, and serves as emergency power supply in the vehicle to home system. Then we have the second technical component, the wall box. The wall box has also to be very specific for this case. We have charging. It is generally a charging device for controlling charging operations to the BEV. But if you look closer, we have to make a distinction between the AC wall boxes and the DC wall boxes. DC wall boxes with higher power rates for charging the vehicle, and also conventional wall boxes and bidirectional charging wall boxes, or wall boxes that can provide or operate with certain protocols that enable bidirectional charging applications. What you see here, the ISO 15118 and the CPP, Open Charge Point Protocol, are standards from the European Union, and they are provided to ensure that the car manufacturers and the wallbox manufacturers provide the same protocols and can talk to each other so that the interfaces are secured. Welcome. And the next one, after the wallbox, we have the home energy management system. Of course, if you want to integrate all load flows from the car through the wallbox, you have a battery storage, you have other assets from the consumption side, you have the PV plant, you have the grid connection, you have to bring in some kind of central intelligence into the home energy management system to coordinate all these load flows and to find also an optimization of these load flows. So this is the part of the HEMS system. So for vehicle to home, you need a HEMS system that coordinates all these load flows. The fourth one, the smart meter. In Germany, we are all at the time running out or rolling out smart meters. And this is a very critical infrastructure for also vehicle-to-grid use cases, because without the smart meter, we have not the interface to the electricity grid, so we cannot provide, for instance, time-of-use tariffs from the grid for vehicle-to-grid use cases. So all of these assets are important that finally bidirectional charging is working. And just a last slide to the status quo. Where are we today in Germany? There are still some barriers that need to be overcome. We have, as I already said, the product standards already defined, the OCPP protocol between wallbox and the BEV. So now, when these protocols are there, the manufacturers, they can follow these protocols. So from now on, I think they were established in 2023. So we expect in 2025 that a lot of more vehicles have the capabilities, and also the wallboxes follow the protocols, so that the use cases are expected from 2025 to get marketable from the vehicle to home side. Vehicle to grid is a bit more complicated. We expect them later, but from 2025 on, bidirectional charger gets more and more important from the marketable solutions we will see there. On the right side, I've provided some data from the bidirectional charging models, or the cars that actually provide some use cases already. You see here the V2L, the vehicle to load, or vehicle to home use cases that are already possible. However, we have still barriers. In Germany, for instance, the missing national regulatory framework and the technology diffusion and prices. If you compare a bidirectional charging wallbox to a conventional one, it's factor 3 or 4 higher. So it's also a pricing issue today. I would like to go on and talk a little bit more about the data we used for our simulations we did in the last week. And what we need for the simulation tool are 4 main components that I would like to break down on this slide. The first one is the household consumption. So we have a reference household with a load profile and a resolution of 50 minutes. That's the input data we need for the tool, with a duration of the whole year, so from January to December, and a daily driving profile of the BEV. That's more a behavioral aspect, but Tobias will talk about this later. On the second part, we have, of course, the PV system we have to define for the household. There we use the typical installed kilowatt peak installed on a reference household. The generation profile is needed in a resolution of 15 minutes and a duration of the whole year. There, thankfully, Amanda provided us some data also from the generation profile and the load profile we used for a simulation of the Brazilian household. Then we have a third component. It's not switching. Yes, the BESS system. So the typical installed kilowatt hours of in the household for the battery storage, the home storage is this, and yeah, you use the capacity in kilowatt hours, the minimum state of charge, and the minimum and maximum charge power is also defined in the tool. And then we have the battery electric vehicle. There we have the capacity which we define of the storage in the BEV, the minimum state of charge, the minimum maximum charge power of the BEV, and the charging and absence times. So when is the car available and when is it not available at the house. And what the initial step was, of course, to have a closer look at the data and comparing them. So what we did here is to have visualized the generation profile of the solar generation in Brazil and in Germany. We have here in Brazil a 6.8 kilowatt peak power plant with an energy yield of 8,740 kilowatt hours. In Germany, in the reference household, 10 kilowatt peak and an energy yield of 10,400 kilowatt hours. And what you can see in this graph is that we have throughout the seasons from autumn, winter, spring, and summer in Brazil a relatively constant daily load profile. This is for each season the medium or the average daily load profile. So no big variances between summer and winter in Brazil. And if you look at the generation profile in Germany, that's very typical. We have very good summer and spring, but the autumn and the winter is really bad. So we have a lot of cloudy days there, and so not a lot of PV generation in the seasons. And we also see it, we have, of course, the plant is higher, but the energy yield is even closer to each other. So the PV system performs, of course, better here in Brazil. Here it's again the same data, the typical amount produced per day as an average displayed per season. And you can see again that autumn and winter is very bad performing in Germany. Then what kind of input data did we use for the reference households? On the right side, the German one, reference household with 4 persons, an electric demand of 11,100 kilowatt hours per year. Included is a heat pump, then the consumption of the battery electric vehicle of 2,738 kilowatt hours. That is calculated with a specific consumption per 100 kilometers and the distance that we expected for the vehicle to drive per day. Then we have a capacity of the BESS of 10 kilowatt hours and a depth of discharge of 10%, minimum depth of discharge. And for Brazil, we have the data from Amanda with 2 persons, electric demand of 11,590 kilowatt hours, consumption of the battery electric vehicle of 657 kilowatt hours, because we got literature from Amanda where it's calculated for medium or average value of 9 kilometers per day. So it's lower than in Germany, but we can, it's a set of parameters we set for this calculation here based on the literature. The capacity of the storage is just half the storage we have in Germany, and the depth of discharge remains the same. Then equal for Brazil and Germany, we set the BEV. So we have on the technical side a charging power from 1.38 kilowatt to 11 kilowatt maximum. We have a capacity of 58 kilowatt hours, so the battery storage in the car, and a depth of discharge, minimum depth of discharge from 30%. And from the behavioral side, we have an absence on working days from 8 a.m. to 5 p.m. and on the weekend from 5 p.m. to 6:30 p.m. Now Tobias will continue with more details concerning the results of the simulation.
So let's go further on with the modeling approach and what methods are we use there. First of all, we build up the modeling tool as a black box approach. For example, we have on the one side, as Lukas already said, the household with the PV profiles, the consumption profiles, and maybe the heat pump profile, or here in Brazil you have more cooling system. On the other side, we have the settings we set for the electric vehicle. As already said, the battery capacity, the depth of charge, discharge from the batteries, the charging power, the charging periods, and also the daily range. And we put it together, all these two energy flows in the system, and create their charging strategy and give all these different energy assets different prioritizations. So, for example, the home storage or the BESS has a higher priority, for example, than the BEV, and so we can have different decision logics for the energy flows in the system. I show you on the next slides more about it, and we had also the differentiation in the system. We can build up a system for a bi-directional charging system and also for an unidirectional charging system where the car only is a consumer of electricity in the system. And these all components or boxes brings together our reference household with a simulation tool, and now have a deeper look in the charging strategies and priorities for the load flow, for example. So we set up 30 different charging cases in the simulation tool, and there we have a consideration of the PV surplus loads, the grid consumption, and also the storage capacities, like the state of charge of the storages. And there we also have the bidirectional discharging case with the power of the PV system. And we have also charging and discharging priorities. For example, as I already said, the home storage has a higher priority than the BEV. That's the case that we want to maximize the self-sufficiency in the system. So we get a higher degree of self-sufficiency when the home storage, for example, is more often full than the BEV, for example. We have also some charging cases that the BEV is only prioritized for charging to ensure the range we need for driving and mobility, for example. And on the other side, we charge or store the energy only with PV surplus energy in our system. And here, for example, I show you the case 17, for example, when we bidirectional discharge energy from the system. First, here's a very simplified charge animation, for example, when the BEV is available, when the BEV SOC, state of charge, is sufficiency, full loaded. We can, and also have PV surplus, or we have no PV surplus, and then we can discharge, for example, the BEV. For example, here's a little simplified animation. We have here the generation, but from the PV system, and when the PV power is not enough to power our demand, for example, the load or the heat pump or the air conditioning. In this case, can we put up the BEV charging power back into the house, and so we can power the house with for the residential energy demand. And now we come to the first results of our simulation tool. For example, for the German household. So what we can see here in the chart is an exemplary summer day in Germany, for example, for a day in August. So we can here see in the areas the energy power of the different energy assets, or for example, in gray the grid power, in yellow here the PV power with the PV surplus, for example, and we also can see here in the dotted lines the state of charge of the home storage, or the BESS. And we can see here the BESS, the home storage, is fully charged. So we have here the opportunity that we can charge the BEV with the surplus energy from the PV system. And so we can here see in blue the BEV state of charge to fill it up. And then have we here the absence times, for example, at the weekend from 4 o'clock to 6 o'clock, for example. And then we can see, okay, it's discharged because of mobility. And sorry. So we have here a little bit, this is also an interesting point. We see here the grid feed in because we have a little bit surplus PV generation, but it's not enough to fill it in the electric vehicle, because we need already 6 ampere to load the electric vehicle. It's a minimum charging power that we need. So in the time when the BESS is not available, the BEV is not available, the home storage can power the household, and when the BEV comes back, we can supply the household with the electricity from the electric car. What we can see here is the results from the simulation from the whole year. So we can see the self-consumption or self-sufficiency is 52%, and compared to a system with an unidirectional vehicle that only gets its energy and not feed it back into the system, have an increasing over 3%, and self-consumption are 68%. We also see the full charge cycles of the BEV, and also the full charge cycles of the home storage system. And what we can see when we compared the bidirectional charging system to the unidirectional charging system, we can see that the bidirectional charger reduces the full charge cycles on the home storage, and also the BEV full charge cycle is increasing only slightly, a little bit. So on the other hand, I show you or the opposite. For a winter day in Germany, we can see here that we have less power PV production, for example, and we have a lot higher energy grid demand, for example, for heating, or mostly for heating stuff. And what we can see here, at the beginning of the day, we have the home storage, or the BV SOC is very low, it's at the minimum, and so we can't discharge energy back into the house, and also the home storage is empty. So we need the grid supply, for example. And what we can see here is the absence times from the BEV in this time, and when the car comes back, we must charge it prioritized because we must ensure the minimum range for the electric vehicle for the mobility. Here the same results of the yearly simulation in Germany, and you can see also the low degree of self-sufficiency on this winter day, for example. So now on the other hand, we do it here with the data from Brasilia, and here you can see an exemplary winter day, for example, with a high PV production, and it's a day in August on the weekend, for example, and in the beginning we charging here the home storage, for example, and then we charge the electric vehicle because the home storage is full loaded. So you can here see the higher prioritization of the home storage, for example. And when the vehicle is absent, maybe for driving. We can see here the grid feed-in with the PV surplus, and also the discharging of the home storage. And when the cars come back at the home, we can supply the household. And over a year in the simulation, we see a self-sufficiency of 46%, and we can increase, compared to an unidirectional system, that we have an increasing about of 8%. And self-consumption with 66%, it's also increasing about 10%. On the other hand, we have here an example for a summer day in January, for example, here in Brazil. So we can also see, for example, here in working day, there we have assumed longer absence times for a working person, especially from 9 to 5, for example. And it's, the logic is very similar to the German systems. So bring it together in the conclusion at the end. So what do we see is the increasing potential of bidirectional charging in general, the results in cost savings in the end of user and for the end users, and the flexibility for the grid. As Lukas already said, the regulatory framework in Germany will become expected in the next years, 25 or 26. But we have to overcome some technical hurdles and the manufacturer hurdles of the BEV and the charging stations. The learning outcomes from the vehicle-to-home simulation is that bidirectional charging can enhance self-sufficiency of renewable energies, reduce electricity costs, for example, and also the grid ease grid load, for example. And also the amount of the increased energy efficiency depends on the framework conditions, for example, such as the user behavior, especially the consumption profile or the driving profile. And on the other hand, also the strategies we used in the simulation tool, like the prioritization of the different energy assets. Maybe we can there also later discuss what maybe make more sense. So finally, the results confirmed the assumption that the vehicle-to-home systems performs better here in Brazil than in Germany, despite of the smaller PV system due to the better solar conditions. We can see it, we have a higher self-sufficiency over 8%, for example, but we can transfer the simulation model in both countries. So here's some points also for the discussion. We had lots of assumptions in the simulation. For example, we had no consideration of external charging, that we assume that the car is only charging in the home. We also have timeability restrictions because we can only use the car when it's at home, and we had a lot of static parameters, for example. So we set no dynamic driving profiles, for example. We had a fixed schedule, and this can also be developed more in the future. And some points for discussion are the use of additional load profiles, for example, to validate also the results of findings of the household, to ensure the transferability, for example, and also to add a feature, for example, for time of use tariffs. This could be also a nice feature, and also some more operating strategies, for example, to change the decision logic, for example, give the BEV a higher prioritization for before the home storage. So before I come to the discussion round, maybe want to say thank you to you all, and also to the Probal project and you from the photovoltaic and photovoltaica. Thank you very much for your attention, and we are happy.
Looking forward to discuss.
Yeah.
Thank you, you both. It was really nice that you already could like read some data and present to us. That was really interesting. Thank you very much. For those who doesn't know, the data that they use from Brazil is from the 0 to 1 project from ENGIE, that where we had a battery installed in some houses in Brazil, in Florianopolis. Where is the one they use from one house? From Praia de Fora. So it's in Florianopolis, so the radiation that we are seeing is from there. If you have any questions, I can also translate it, but I have some. What do you think, like, I'm trying to buy an electric car and my biggest concern is how the degradation will be and the value of the car and everything. How do you think that would be affected by bidirectional charging, like how people would see this?
Yeah, we see it in the simulations. Full charging cycles are not very high, for example. So also the loads for the cars not high. When you're driving the car, you have a lot of higher power you need, for example, for driving. But the household doesn't have very high peaks, so it's not stressful for the car.
Oh, good.
Yeah.
Good point.
Yeah.
In the global technical regulation number 22, there is this new value like virtual mileage. And this is what you mentioned, if you will charge or discharge your car at home without driving, then you have like this virtual mileage, and this is for warranty topics and also for aging and battery degradation topics. So this is like a calculation. You have the energy consumption and the time, how long the battery is charging or discharging, and then you can calculate like this virtual mileage. There I can show you how this is calculated, or this new regulation.
Yeah, but I still like, yeah, good point. There is a lower power, and okay, you can calculate it, but it still concerns me. Could you come back to the graph before? The last graph, no, the before last graph. That is very cool. The interior? Ah, yeah, that's weekend, right?
Yes.
So the next one.
Ah, okay.
Yeah, this one. So I thought that would be the first thing that you were going to show it. That would be this peak during the night that we have in Brazil. That's very typical in Brazil because we have electric showers mostly. So everyone arrives home and take a shower, and that's a big peak for us, or take on the television. And then I thought that would be like the role for B2G, like to fill the grid with vehicle to charge to home, and then you can charge it during the night, like during the rest of the night. But here you're mostly using like the simulation to charge the car and not to provide for this peak. Why do you think in this scenario is not happening this?
Yeah, our target was to increase the self-sufficiency and not to cut the load peaks, for example. But it's other research question, for example. But yeah, we also can implement it. But what we can see here, the capacity of the BEV is not enough to puffer or cut this load peak off. But it's maybe a useful
And maybe
option.
if you put tariff of use, that would be prioritized, like that would be
could be also an opportunity. Our main focus was already set the self-sufficiency. So, but we also can do some financial analysis. For example, when the tariff is cheap at the night, for example, we can put the energy into the car and feed it back when it's or to cut off these load peaks.
Good. I have like, the plan is to do simulations and maybe write a paper about it, and then I have some pointers afterwards for like the data that we are using. Maybe we can try like this 9 kilometers per day. Okay, it's a literature, but like it seems so small.
So they are using 9 kilometers per day because I sent this information from him because it was what I found on Brazil internet and something like that. And when we have a conversation about that, before I looking for the kilometers, I say to him, like, here in Florianopolis, we have long distance to go into somewhere. But in like big cities, normally people, it's like you spend a lot of time in traffic, but it's not like so far away. And this is average for the whole Brazil. Yeah, so I am defense a little bit you because I know she will talk about it.
Yeah, but we can adapt it. So we can. Yeah.
It seems to be a funny question, but what about you work with? It's just 100% electric vehicle you are working on? Have you considered a hybrid plug-in ones whose batteries is nearly the same as you have in the households and things like that? Have you considered it or not? Because if the priority is to keep storage on the house, so this is something that could be considerable. But how do you think? What do you think about it if you were working on that area?
I think, I don't know if I understood the question right, but the main idea here was, of course, to increase self-sufficiency. And this is the main application that this tools provides. What we could think in the future is to combine it maybe with other applications that are combined in the tool or that so are also considered, as you said. Yeah, but the main focus was first to get the self-sufficiency optimization working, and then, of course, other use cases and applications make sense to see how they perform with the tool, or how can they be added to the tool. Yeah.
Okay, I have maybe a question which will go in the same direction. So can you please jump back to slide number 6? On the right-hand side, I can remember there were some numbers. Yeah, slide 6. Okay, maybe you can remember on slide 6 on the right-hand side, you showed numbers for BEVs and I think for photovoltaic, and I think at BEVs there was like here we are, plus 1,170%. Where does this number came from and what does it mean?
This is the increasing number of new electric vehicles in the market from 2015 to 2020 in the European Union.
European.
Yeah.
Okay, then my next question, are you dealing with a prediction? So what will happen in Germany maybe in 2025 or 2030? Are you dealing with this topic, or do you only have a look on the moment, what happens in 2024 or maybe the last years where you have the data?
Here we have only look at the moment, but I think, Lukas, you have seen a little bit in the future the increasing number of electric vehicles are
increasing. Yeah, and I think what I've seen in the literature research in the past days was that was that there are some hurdles that need to be overcome, and the expectations are from 2025 or 2026 onwards with marketable solutions, whatever that means. But as I understood it right, we have worldwide nowadays about 150 demonstration projects in bidirectional charging worldwide. Increasing number of demonstration projects also. But I think the step into the market will come in the next year, but we will never know what the future will foresee. But yeah, what I see is that there is more research in this topic, and there is more on the side of the regulatory framework, more ambitions that interfaces become standardized, and that the parameters are set so that everything should work in the next few years. Yeah.
Thank you.
Sorry, it's not a question actually, it's just an idea that I had now. We have some line of research on here, it's about site adaptation and things like that. So my suggestion is we can select one day, like one clear day, one cloudy day in each Brazil and Germany, and each season to see exactly, like, for example, you showed me January, and it's not a good January actually. I pay attention, it was like very cloudy. So or maybe we can do like one clear day and one cloudy day per month, maybe, to Brazil and to Germany. Just a suggestion, because everyone just make like a lot of questions, and I was thinking because the graphic is not so good, in my opinion. It's the reality, but it's not like the reality for Brazil. Maybe this year was like so cloudy on January.
Yeah, I think it's a good point. We can also do it. We only took example days, and yeah, we can change it to every day of the year. Yeah, it's no problem. The
visualizations are more the visuals we showed is more like to understand does the tool work properly, and the numbers that are calculated, the self-sufficiency, are based on the whole year. So that is something we have to distinguish. We could also think about calculating for these specific days then daily parameters, self-sufficiency or medium average self-sufficiency in a season to distinguish between the seasons for a country and then between the countries.
Any questions? I think it's allowed as well. Thank you very much, guys. For those who have more questions, we could grab a beer later. And have a nice trip back. Thank you very much for coming.
Thank you.